Okay, welcome back to video 2.
You're not really welcome.
I didn't leave much room for 3. I don't know why I didn't do that or why I did that, but we'll get around it. So this one says a circular ring is heated so that it expands. If the rate increases, if the rate of increase of the radius is 0.01 centimeters per second, so that's a rate they've already given us in these ones now, right? Determine the rate at which the circumference is increasing. So now these problems from now on, they're going to have 2 rates that we're dealing with.
It
So,
only expands so much. That's assuming the guy
Okay.
doesn't sell it, but it's half decent.
so for pretty much all of these, they're now going to be ddt again, right? So you can see this centimeters per second. Really, we're caring about like how fast these things are happening over time. So this is the rate that we're dealing with now. So it says radius and circumference. So the formula that we want to start off with here is going to be c is equal to 2 pi r. You pretty much want to find a formula for any of these first. Like that's going to be your first step, right? And we've got 2 variables. So the variables we have are c and r. We also have different rates. So the rates that are involved here are going to be the derivative of circumference with respect to time, and the derivative of the radius with respect to time. So those are the 2 rates that we're dealing with here. What rate would this one be?
dr over dt.
Right, that is that one. So we know that one already. The question is asking us, what is that one? So that's what we're after in the end here. Okay, so what we're going to do is actually just take the derivative of this. So ddt of this, right? Both sides. Now, here, let's, I'm going to split this in half down here and say this is question 3. So we're going to finish question 3 down here. Okay, now if we do that, we take the derivative of that equation up there, that's going to turn into dc over dt, which is the one we want, right? That's the one we want, so we're after that. And that's going to be equal to, now if we take the derivative of this, that's going to be 2 pi, and just 2 pi, right? But, do you remember that implicit differentiation thing we did?
No. The name I remember.
Is, you remember? Remember when we took a derivative of something, and then, so the derivative of this is just 2 pi times 1, right? So 2 pi times 1. But then it's also going to be multiplied by the derivative
Of the inside.
dr dt, right? This is just the chain rule, so it's the derivative of the inside. Yeah, good call. That's going to be the general setup of all these questions. We're going to have 2 rates. We're going to have, you know, that one and that one. One of them is going to be given to you in the question, and we need to solve for the other one.
Cool, we almost have everything we need to figure it out except for knowing what we're doing.
So we do know this though. We know this number already, right? They gave it as the question, so we just gotta fill in the blanks. So dc over dt is equal to 2 pi times 0.01 centimeters per second. So the rate at which the circumference is changing is going to be
0.02 pi centimeters per second.
0.02 pi centimeters per second, yeah. So that's 3.
Now we know.
Now we know.
I
All right,
don't
let's-
like that you're recording this because now I can actually physically see how much time I waste.
Yeah, I do like that. That's good. All right, 4. Okay, so this same disk is now cooling. During the cooling process, the radius is found to be decreasing at a rate of this. So we're just cooling it now. What rate is the area of the disk changing when the radius of the disk is 100 centimeters? So now it's cooling. and we're talking about area instead. So the formula for area of a circle is A is equal to pi r squared. So that's step number one. Step number two is figure out the variables that we're dealing with. So variables here are A and R. The rates that we're interested in are going to be dA, so the rate at which the area is changing with respect to time, and dr, dt. Right, so now we're just going to do really the same thing. So now we're going to take the derivative, so ddt of this entire formula, and that's going to be dA dt is equal to pi times 2r, not 24r, dr. Okay, and if we, I'll just kind of rewrite that a little bit better. dA over dt is equal to, let's write that as 2 pi r dr dt.
I'll just wait until I can see the board.
Oh, you can't see it?
That's how I wrote it.
You got it?
Yeah.
Okay. Now that's the second part of these ones. This one we just had to put in the rate, right? In the last question. We have the rate of cooling for this one too. Was this, right? That's how fast it's cooling. But we also know radius at that point. So this rate is actually changing. It's going to be different at different points, right? So we know r and we know dr dt. So now we're just going to fill in what we know again. So dA over dt is going to be equal to 2 pi times 100 centimeters, because that's what it said the radius is at the point that we care. And then the rate that we're talking about is going to be 0.02 centimeters per second. And I purposefully made a mistake somewhere. What have I not done? Could this rate that I'm talking about here,
Well,
the rate at which is changing, could it be increasing or decreasing?
It has to be decreasing.
How would we show that mathematically if something was increasing or decreasing?
Negative 2 pi.
Negative, right? So where the negative comes from though is from this, right? Because in our question it said the rate at which the radius is decreasing is 0.02 centimeters a second. So that decreasing means it has to be negative. So our answer is going to be negative as well, meaning that it's decreasing. So that's going to be negative 4 pi centimeters squared per second, which makes sense, right? We're talking about the derivative of the area with respect to time. So area over time, that's a rate. Okay, next one.
That's a thing I was talking about, like putting bearings on shafts.
Yep.
Yeah, when we're out in the field, we just use a big freaking hammer.
Big hammer. Yeah.
We only do that when we have like equipment in the yard.
Okay, we're gonna skip 5. Let's go to 6. Okay, so it says an object is moving clockwise around a circle, and it gave you the formula of the circle. As it passes through the point 6, 8, the y-coordinate is decreasing at the rate of 3 units per second. At what rate is the x-coordinate changing at that point? So just want to draw you kind of a circle of what's happening here.
Is tomorrow double physics?
Yes.
Ashley's not going to be here, so we can work.
Oh, actually?
Yeah.
Huh.
She's going to Edmonton for handball.
Right.
So if Rachel comes.
Okay, so here's what's happening. It's saying that there's that point, it's going around a circle. It's saying that the y-coordinate is decreasing at a rate of 3 units per second. So as this thing is going around the circle, the y-coordinate would change to 5 in 1 second, right? The question is how is the x coordinate changing as that thing's going around the circle, right?
In a similar fashion.
Right. So what are we gonna do? We've got a formula. What are we probably gonna have to do with that formula?
Probably the derivative.
Probably gonna find the derivative. So if we find the derivative with respect to what?
The monkey's arse. I don't know.
T.
Time.
Because it's talking about rates per second. So derivative with respect to time. We're gonna take
always DDT.
Pretty much is. It's for the most part it's gonna be DDT for most of these. So the derivative with respect to time of this formula.
We read that as 10 squared just to make it more complicated.
And before I do that, I just want you guys to get in the habit of writing down the variables. So the variables involved here are going to be x and y. And the rates that we're interested in are going to be dx dt and dy dt. Those are the two rates, right? We know y, we know this one, right, from the question. We're looking for that one in the end. Okay, so carrying on with this. If we do that, you get 2x, and now implicit differentiation again. What's going to be tacked on beside that? 2x times what?
dx dt.
Right, dx dt. Plus 2y dy dt
Oh, we didn't have to implicit differentiate x.
is equal to 0. The reason why you wouldn't have to before, because it was x, it was over dx, right?
Oh.
So both of these are with respect to t. So that's why you have to do that for both of them in this case now.
Now we know.
Now we know.
Equals 0.
Equals 0, yep.
What if we wrote that as 10 squared?
Okay, now with these ones, we just kind of, let's fill in what we know. So we know this one from the question, right? That was equal to, what was that equal to? A rate of 3 units. And so a rate of 3 units per second going around the circle, would that be negative or positive 3?
Does it matter?
Yeah, because if you think about this thing going around, that y value is going to be going down. It's going to be going back up again when it comes around.
Yeah, but who says, does it specify that it's going clockwise? Oh,
Yeah, it does.
Yeah.
And it says it's decreasing, right, the question. So this is going to be negative 3 when I fill that in.
Yeah.
But I want to solve for this, right, dx dt in the end. I don't know x and I don't know y. Is there any way from the question that I can figure that out?
Range.
But I've got 3 things I don't know so far.
I'll cry. Ask Mr. Brown.
Looking back at the question, is there anything though that like...
You know the point, you know x and y.
Right, I know the point. I know x and y right there. So just plug those numbers into x and y here. So x would be 6, y would be 8. So just putting those numbers in now.
But now you have 0 variables, so now what do we need to do?
We've still got this one. This is the one we're looking for.
Oh, okay.
Right?
Yeah.
So let's plug in what we know. This is going to be 2 times 6 times dx dt plus 2 times 8 times negative 3 is equal to 0. Yeah.
Chill.
So now all you gotta do, I'm just gonna kind of skip this part. Dx dt, if you solve for that, is gonna be equal to 4.
That's like the fastest I've ever typed something to a calculator.
4 units per second. Yeah. Now what does that mean? So 4 units per second, we figured that out. Is our x coordinate here, would that be going up or going down? Would it be increasing or decreasing?
Decreasing. It's going clockwise. What's negative 4?
But it makes sense if it's at this point, right, up here, right? It's kind of going through this spot. X is going to be going that way, right?
Oh yeah, I guess so. Yeah.
X is going to be increasing, and that makes sense. We got positive for units, so that's what that's telling you. The symbol up front is saying that X is increasing at that point. It's going up. So
Just like my first marriage, couldn't see all the signs.
It's gonna be funny if I show this video like later years. Kids are gonna be like, "What?"
Oh, I don't care.
They're probably gonna know you.
So,
All right, last question. Okay, so it says water is being poured into an aquarium that is 60 centimeters long, 30 centimeters wide, and 40 centimeters deep. Determine the relationship between the rate at which water is being poured and the rate at which, maybe I'll do the rate and the rate, at which the depth is increasing. So in this case, they didn't give us a number for rate. We just need to come up with an equation in the end is what we're after, right? Okay, so if I draw a box, oh good.
don't forget to draw the fish.
Oop. Don't forget to draw the fish.
Can name him Gilbert. In later years, it'll be like 2 years before you calculus anything.
Alright, Rachel, don't make fun of my box. Okay, so the rates involved here.
Where's the fish?
Actually, let's do the formula first. Volume. Oh yeah, fish.
Yeah.
Excuse the interruption. There will be saucy burgers for sale lunch today. Saucy burgers with strawberry shortcake.
Okay, so we got our fish tank. The volume of our fish tank, the formula for that is really just going to be length times width times height. Now, the length and the width, we don't really care about, right? We're talking about the rate at which when water is being poured in, so that's volume, right? And the rate at which the depth is increasing. So we're looking at H as the depth, right? That's the one that's going to be our...
Figure out volume though, because it gives us length.
But we want a rate, not just the volume. We want the rate at which it's changing.
This is confusing, but alright, keep going.
Yeah. Okay. So we care about height. That's the one that's changing, right? H is going to be changing. Length and width in this case. So the length and the width, like those two dimensions, aren't changing at all, right? We're talking about the height. That's the one that's going to be filling. Like our water is filling up over time. So we've got volume changing over time. So if we write down our rates, let's do that. So rates that we're caring about are going to be the rate at which volume is changing over time and the rate at which your height is changing over time. Our variables were, V and H. So length and width are staying the same. Height's the one that's changing, right?
Yeah.
So if we kind of fill in what we know, the length of this thing, except from the question, was 60. It was 30 meters wide, or 30 centimeters wide, and then height is the one we care about. So I'm just going to write this one more time with those multiplied together. 1800 H. Now all we got to do is take the derivative with respect to time. ddt of this entire equation. So if we do that, we end up with dv over dt is equal to 1800 and then just dh dt.
That's it.
And that's it. That's our relationship.
Cool. Now
So
we just gotta account for the rocks in the bottom of the tank.
Right. So the volume, the rate of at which the volume is changing, is 1800 times more than the rate at which the height is changing over time.
That seems so complicated and so simple at the same time.
Okay, see you in class. That's the end of this video. We'll pick up on question 8 tomorrow.